Hello, my name is Jan Dubiński, and I would like to describe to you our active defense framework against encoder model stealing and outline the first task of the hackathon, as those two are closely related. In a supervised machine learning API, a user selects a data item such as an image and sends it as a query to the API. The API then responds with a low-dimensional output, such as labels or softmax scores. In a self-supervised learning API, a user again sends a data item to the API. The encoder model behind the API extracts the most important features of the input, and the API returns a high-dimensional representation. The user can then use those representations to solve a particular downstream task. For example, a small company interested in a plant classification product can train only a classification head, relying on the representations returned by the encoder API. However, high-dimensional representations reveal much more information about the encoder model behind the API than low-dimensional outputs, such as labels. This makes encoder models much more prone to model stealing attempts. In a model stealing attack, an adversary queries the model API and gathers input-output pairs not to solve a particular downstream task, but to train a local stolen copy of the model. This requires significantly less resources than training the model from scratch. Up until now, existing defenses against encoder model stealing have been reactive, enabling ownership resolution after the model was already stolen, or lower the utility of the encoder for its legitimate users. We propose the first active defense method that hinders model stealing attempts without reducing the utility of the encoder model for legitimate users. We named our method Bugs for Buckets. We base our method on the following observation. Queries from legitimate users occupy a single region of the representation space, as the users utilize the encoder to solve a particular downstream task. However, an attacker must query the entire representation space of the encoder to steal the full functionality of the model. With this observation, the main idea of our method is the following. We divide the representation space of the encoder model into buckets. We monitor the number of buckets occupied by user queries and associate negligible cost with small coverage and a very high cost with high coverage. But how do we divide the representation space into buckets? We employ the locally sensitive hashing algorithm to monitor the coverage of the representation space of the encoder. After applying a hashing function to the representations returned by the encoder, each representation is assigned a hash bucket. Similar representations are hashed into the same bucket. These similar representations are assigned different hash buckets. For each user, we monitor the number of unique hash buckets occupied by their queries. Here we can see the percentage of unique buckets occupied in relation to the number of queries sent from a different dataset. For legitimate users, represented as querying from Cypher10, FMIS, SVHN datasets, the number of buckets occupied quickly saturates. For the attacker, however, who queries from a diverse dataset, such as ImageNet, the number of buckets occupied grows quickly and saturates slowly. Once we have the number of buckets occupied for a user, we can map the coverage of the representation space to a cost. We express this cost by adding noise to the representations returned to the user. This lowers the utility of those representations. We tailor the cost function in such a way that a negligible cost is associated with coverage of latent space displayed by legitimate users. However, the function increases very sharply after a certain threshold is reached. This prevents the attacker from training a stolen model copy. This is because the representations they received are heavily noised. Overall, our B4B works as follows. First, we obtain the representation for a user query. Then, we measure the coverage of the latent space from queries sent by a user. We map this coverage to a cost, adjusting the utility of the representation by adding noise. So, now allow me to describe the first task of our hackathon. There will be an encoder model trained on a particular dataset. This model takes images as inputs and outputs high-dimensional feature-rich representations. Now, your goal as participants will be to train a stolen model copy. Now, this is the general framework for model stealing. An attacker takes an input data query, sends the same data points to the victim model API and to the stolen model copy, and they maximize the agreement between the outputs from the victim and the stolen model copy. Of course, the victim model will be hidden behind an API, so it will be a total black box. The model will be also protected by our adaptive noising mechanism. To sum up, the task is to steal a protected machine learning encoder model that's hidden behind an API. The goal is to have a local model that outputs representations that are most similar to the representations returned by the victim model.